Good morning, all. Assalamu alaikum. We start in 3 minutes. All right, good morning, everyone. I'll just ask the first person on the list, Ahmed Arabi, can you please confirm if the audio is clear? Or Aladdin? Or anyone, actually? Yeah, yep, all clear. All right, let's make a start. So welcome to the second session. A few weeks ago, we started off the first session speaking about an introduction to architecture and the architecture course. We're going to be conducting these sessions at least at a try every 3 weeks. Every couple of weeks. Every couple of weeks, we're going to pick up a topic that has to do with architecture and speak about it. And today we're talking about S.O.L.I.D Design Principles. And the reason we are, well, it's not purely architecture, it's also very relevant for developers as well. That's why we chose this one for today. For those who weren't here last time, my name is Omar Bseiso. I've been an architect for a little over, I don't know, maybe about 15 years now. I've been in this industry for a little above 20. I spoke in few conferences. My job on daily basis is running a company called Cloud5, which offers architecture services as well as development services. This is my passion. This is what I do. And in my free time, for those who know me, I'm a bit crazy, and I just like putting computers together that you know, people usually say that I have too much time on my hand. I like building fast computers. It's a hobby I can't get rid of at the moment. Let's make a start. So what is S.O.L.I.D? A lot of people refer to S.O.L.I.D, refer to design patterns. I'm on a lot of social networks, including Twitter, Facebook, Clubhouse, and people talk about S.O.L.I.D and design patterns all the time. Sometimes these discussions are not really based on definitions and based on true understanding of what S.O.L.I.D is. So let's start today by defining S.O.L.I.D. S.O.L.I.D is a mnemonic acronym for design principles that are supposed to be used by architects and developers to make the code or designs more understandable, flexible, and maintainable. I want to stress on the maintainable part. The maintainable is what matters the most. In our introduction to architecture, it was very important for us to understand that part of the architect's job is to basically make the design responsive to change. Bugs are inevitable, technology changes are inevitable, requirements changes are inevitable. And that's why one of the most important things is to make the code maintainable. We spoke about the ISO standard in the last time we met, and we said that part of the ISO standard is actually one of the major metrics is maintainability. And by maintainability, we don't mean something like you would do to an air conditioning, but more something that happens every day, and that is change. And change for us is the major aspect that as architects, we aim to be able to respond to. So continuing on that principle. Sorry. Let's talk about the S.O.L.I.D principles. So the first one is single responsibility principle. What does that mean? We'll get into it in a second, but it basically means that an object or a class or a component in your system should only change for one and one reason only. Next, we have the open-closed principle. The open-closed principle means that your code should be open for extension, but closed for modification. Meaning that usually, if we finalize a piece of code, if we've tested it, and if it's made it to production, we basically leave it alone. The third one is called the Liskov substitution principle. And that is basically saying that subtypes and supertypes can be interchangeable without a major change to the results of an algorithm. And we're going to get into that in a sec. Interface segregation principle means that every consumer needs to have an optimized interface for its usage. It means that we cannot enforce on consumers operations that they cannot implement. And number 5 is dependency inversion principle. And I'm sure a lot of people here, whether you're doing front end, back end, or anything in between, have done dependency injection. And it's basically the idea of inversion of control and that every dependency is built on an abstraction. So we'll get into each one of these in a sec, but first a bit of history. S.O.L.I.D was promoted by Robert C. Martin. Robert C. Martin is a software engineer, an American software engineer, and he introduced the S.O.L.I.D design principles in 2000, and it was called Design Principles and Design Patterns. A lot of people think or mistakenly think that Martin came up with the actual design principles. He didn't. In fact, the Liskov substitution principle was actually invented by Barbara Liskov, and the open-close principle was invented by Bertrand Meyer, who's a French developer. A bit of history on that is important because, again, people think that the S.O.L.I.D design principle existed as long as design patterns. They didn't. In fact, just like everything is a trend today, and we see all these frameworks becoming a trend, patterns becoming a trend, all of the stuff that we see today trending over Stack Overflow or over GitHub, the same situation was for S.O.L.I.D. But the fact is, S.O.L.I.D trended in 2001. there was a manifesto for agile software development. Yes, believe it or not, it was an agile software development paper that actually included the first S.O.L.I.D principles. So I can't stress enough that the reason we're going through this today is, again, our primary concern is being able to respond to change. Our primary concern is to be able to deal with the inevitable case that change is always going to be there, whether on a requirement or a technology, or even from a maintenance perspective over time. So let's start. Single responsibility principle. Definition-wise, the single responsibility principle is basically a rule that every module or class must have a responsibility over a single part or functionality of the software. I personally find this definition a bit cumbersome. So to me personally, the SRP is basically means I should only change a piece of code for one reason. For one reason and one reason only. And this is where people start thinking, okay, so I code up a class and I have one reason to change it. But reality is I have a lot of classes which do a lot of things. So for example, what do people think about entity classes? Unit of work, WCF services, web services, REST services, you name it. The idea here that when you code up that class, the entity class, it should only change if the structure of the entity changes. That is your one reason. Now, if for any other reason your entity class is doing any other responsibilities other than that, then you might want to rethink your class. An entity class could encapsulate, an entity class by definition encapsulates structure and behavior. If you're doing a calculation in there, you abstract it to another class. You take it to another utility. A unit of work. A unit of work is basically a concept where a lot of operations take place and at the end they get committed or rolled back just like an encapsulating transaction. Again, the unit of work class itself needs to change only if the way that operations are maintained and transacted changes. It should not be the case that the unit of work should have any other logic. WCF services, REST services, MVC controllers, whatever you have, again, should not include any logic. It should change for one reason. When the facade that you're creating with your services changes, when the contract changes, and even that can be abstracted, but when the operations themselves are changed. That's the only reason why you would change these WCF services. So regardless of what you practice every day and you think that some classes are inevitable to have more than a single responsibility, you need to test that theory and go back and say, nah, I actually think that I can do this better. So what's the best way to visualize single responsibility principle? This is your system. Your system is usually a bunch of classes and modules glued together through the runtime to basically execute functionality. The reality is, this is comparable to a Swiss knife if you follow the single responsibility principle properly, because that means that every knife in the Army Swiss knife has got its own functionality that really doesn't do anything else, so it's single responsibility. And if you need to change that knife or adjust it or adapt it to any other, some of these customizable knives, you'll be ever dealing with one component at a time, changing it for one reason at a time, whether to add functionality or remove functionality. But there should be only one change, one type of change, one reason to change that one class. So let's look at some code. And this is the first time in this course that we're going to start looking at some code, but I'm guessing with single responsibility, you need to show some code to basically demonstrate what we're looking at. So this is a typical repository class. Now, if I look at this, I should say that, yeah, this looks pretty simple. I'm inheriting from a repository base, which must have a method called saveEntity. I'm creating a customer, great. So where is the single responsibility principle violation in here? Well, it's in this part for multiple problems. Number one, what if I want to change the file name? Number two, what if I want to log something else other than the message? Number three, what if I don't want to log the error to a file at all? The problem here is, without digging very deep, I've identified 3 reasons that I might come back to this class and want to change it. This is not acceptable, because the only reason that I should change a repository class is if the repository logic of persisting or retrieving data changes. That is, in fact, the single responsibility principle of a repository. Single responsibility of a repository. So what do I do as a programmer going from here? Well, let's look at a different way of looking at things. Number one, I introduce an interface called iLogger and include the log exception. Now, this can be implemented in any way I want. Number two is I inject, or let's leave injection out of it, but at least have a method of providing the customer repository with the logger. And number three is my method now uses the logger to log the exception. What I've done here is eliminated the reasons for change that I have to go back to the customer repository unless the core functionality of the customer repository changes. But other than that, all the logging changes are now going to happen in whatever implementation of iLogger I decide to use, whether it's a file, whether it's an event log, or anything else. And this is how I basically removed the violation of the single responsibility principle in here. All right. Now, moving along, we've got the open-closed principle. Actually, I want to ask, does anyone have a question before we move on? All good. So open-closed principle basically says the following. We're never going to build something with the idea that we're going to go back and change it. If anything, we build it so that we go back and we're able to extend it. Why? Change includes regression. Change is problematic by nature in code. And if the core functionality is not changing, and we just want to add certain modules or certain functionality, we should not really be changing the code we've already written. Objects by nature should be open for extension and closed for modification. So again, it's having that attitude that once you write a piece of code and ship it into production, you don't want to go back and change that piece of code. Again, limiting the surface area for change in these classes. So what are my tools? There's a lot. I can use inheritance, I can use composition, I can use abstraction, and I can definitely use design patterns with the decorator pattern or the proxy pattern to be able to add functionality to existing objects, right? So let's move on and do a little bit of a joke. You don't need, this is the easiest way for you to understand this. You don't need an open chest surgery when you want to put on a coat. It's as simple as that. So let's have a look at what this means. If I have an, I'm not sure how this line happened, Muhammad, well done. I'm not sure how to clear this now. Ah, that's Cliff Warren. Okay. Thanks, Cliff.
Oh no, I just put my stamp there. That's somebody else's squiggle.
Ah, yeah, I know. I'm just not sure how to clear it out. That's interesting. Not sure how someone did it, but anyway.
You might be able to clear all illustrations using the annotation tool in Zoom. So if you go to annotations, there's a little rubbish bin.
Annotations.
Oh no, annotations in Zoom.
In Zoom itself.
Yeah.
Where is annotations in Room itself, Cliff? Disable annotation for others. Yeah, that works. Now, how do I clear them?
Oh, I'm not sure. I've got a drop-down menu for view options, but as a presenter, I think it might be different for you.
Yeah, it might be a bit different. That's fine. I'm gonna have to live with it at the moment. Clear all drawings. Here we go. Who said we can't figure this thing out? Now I gotta figure out how to remove it altogether. Here we go. All right, we're back to normal, people. So we've got an enum here, and it says we have a credit card type, and we want to use a method that says, is credit card number valid? It's a method that validates the credit type number. And we use regular expressions to basically say if the credit card number is right or wrong. Now, at face value, if these are the credit card numbers, if these are the credit card types that you are supporting on release on day one, we basically have a situation where we're happy. This code actually works. There is no problem with this code at all. The problem is, as a good designer, you need to figure out that these are not the only credit card types that we have. And credit card types may change. So the fact that we start here and we could end up with adding a new diner's credit card and a new regular expression means that we've violated the open close principle. It means that we need to go back and figure out a way to write this method without the surface area for change of code if we add new credit card types. So how do we go about that? This is where we're going to use stuff like composition. This is where we use stuff like design patterns to figure this stuff out. So let's start the blank slate. Number one, we're going to introduce an iCredit card validator. It's an interface that basically specifies how to validate credit card numbers. Number two, we're going to introduce one of these validators for every type of credit card. So on the screen now, we've got a MasterCard validator and we've got an Amex validator, and we do the same for Visa, we do the same for diners. And at the end, we basically say our method is credit card number valid. Now takes the CC number, the credit card number, but instead of taking the type of the credit card like we did before, we're now taking our interface, our validator that we've created, and we can keep on extending on unlimited number of cards and unlimited logic. And now this method, one might say, if you validate that the credit card number actually exists, one might say that you wouldn't need to change it again. All right. This is the key. Right. So for people who got very scared from the first image that we put with the guy with the open chest so that he can put on a coat, this is another way to think about it. You do not need to rewire your entire motherboard to plug in Mr. Happy. So if you have a USB key, you do not need to go crazy to basically interface with your motherboard or change the motherboard every time you plug in a different USB key with a different storage or different format, etc. All right. So any questions on open close principle before we go on? Okay. Liskov substitution, the cool one. So objects should be replaceable by their subtypes without altering the correctness of the system. Ah, sounds good. What does it mean? Abstract classes have got their places just like interfaces. We've got standards, we've got contravariants, covariants, no new exceptions should be thrown by the methods of the subtype. You read all of these definitions with the Liskov substitution principle, add to that the complexity of the name itself, and you might think to yourself, how do I think about this while I'm coding or designing code? And the answer is, all of this guff simply means one thing. It means that you need to find a way to identify if your abstractions are correct or not. You need to find a way to basically guarantee that you are using the correct abstraction for your logic, right? What's an abstraction? It's when you include an abstract class, you include an interface, and you want to make sure that anything that passes implementing that transaction throughout your system, in no matter how it's implemented, it does not actually alter the system's correctness. That is how you guarantee that you've got the right abstraction. So basically, if it looks like a duck, quacks like a duck, and most probably it is a duck, but if it needs batteries, you've got issues. And that is where you need to think about it. So let's have a look at a concrete example again. Number one, we have a class called rectangle. It's got a height and a width. I want to introduce a class that's a square. What's a square? A rectangle with equal dimensions. So what am I going to do? Say I'm going to put in a square, and I'm going to make it inherit from rectangle. And then I'm going to make sure that when you pass me a width, it's going to be the same as the height. And when you pass me a height, the width is going to follow. All right. Straightforward. This kind of makes sense until we come and introduce area calculation. So when we look at calculating the area of a rectangle or a square, we have height times width for a rectangle and height times height for a square, because it doesn't really matter. And we introduce two tests that will actually pass. There is no problem here. We can get a 2x3 rectangle. We can go a 3x3 square. And these tests will actually pass with flying colors. But does that mean it's the right abstraction? It's only the right abstraction when I can move square and rectangle across and replace them with one another and do not alter the correctness of the system. So let's see how that works. Here is one that will fail. I want a 24 for 4x6 rectangle from a square. So I'm expecting 24, and I'm expecting that using a square, because a square can inherit from a rectangle. We've already established that abstraction here. We've already established that relationship, meaning that I should really be able to go, the rectangle is equal to a new square, and basically get the result that I expect. The answer is absolutely not, and this test failed. Why? Because I basically said that the new... Sorry? Oh, okay, so the new rectangle is a square, and that will not give me the result expected, because again, if we go back, we're going to notice that the area is height by height, meaning that what's going to happen here is 4x4, meaning that my answer is 16, not 24. So this test fails because my abstraction wasn't correct. So how do I get the right abstraction? How do I actually establish the right abstraction? It's not always that obvious. I do understand that. But usually when the abstraction results in such a relationship which is archaic, there is only one thing to think about at this stage. And that is usually that you go a level higher. We need a parent for these two objects. So let's start with a parent called shape. And we're going to give it an abstract definition of a method called area, which returns me back the area of this shape. I'm then going to go ahead and bring back my rectangle and bring back my square. Now the rectangle, in the first example, rectangle was the parent of square, or square was a subtype of rectangle with extra constraints that the dimensions needed to be the same. In this case, we're saying no, rectangle and square are both shapes. And each one is got a different structure to their dimensions, and they've got a different structure, a different methodology to how to calculate their area. But what they do have in common is they're both shapes, and they both have the capability of producing their area. So now the area calculator becomes calculate area of shape and give me the area of that shape, regardless of what that shape is. It does not matter how you test this. Regardless, this will always give you the correct area. It will not alter the correctness of the system based on the type of shape that you pass in. So if we repeat it again, what is Liskov substitution that seems to be the most confusing of all the S.O.L.I.D principles? It's simply defining the right layer of abstraction. In a lot of situations, people mix that up. In a lot of situations, people sit in front of objects in real life and wonder to themselves, how do I model this in a class model that actually makes sense? Right? Any question on Liskov substitution before we move on? If it look walk quack like a duck, then it is a duck, and if it needs batteries, then it's an extended duck. Thank you. All right, let's move on to ISP. Interface segregation principle. Basically, this one says that we're going to split larger interfaces into smaller ones or adapt interfaces so that they fit the needs of their consumer. A consumer can be the consumer of an API with an interface, or the implementer of an interface, or the actual inheritance child, let's say, of an interface. Anything that uses an interface. Basically, the rule says if you have many specific interfaces, it's better than one generic one. Now, I know the people who code APIs around here and who design APIs up here just got a shiver down their spine thinking to themselves, but I'm used to give them the one API that rules them all. I'm used to give them one interface that does it all. How many of you guys have established these interfaces which basically say, I person, I customer manager, I entity manager is even worse. And the story goes on and on. The idea is that we have this thing that if we do less interfaces, bigger ones that cater for everything, we're doing it right, when the reality is absolutely the opposite. People complain about the explosion of classes with SRP. We do not care how many classes you have. We do not care about how much code you have. We care about one thing. Is it achieving cohesion? If you remember from the first session that we did, we spoke about high cohesion and low coupling. Interface segregation principle is all about you being able to identify cohesion. In real life, the way you do interface segregation is almost every day. Where you take your adapter to a new country, you plug in this thing into the wall, which basically gives you new options. You have new interfaces. You have different plugs for different regions. Every day, you kind of abide by the interface segregation principle. You're basically complying with your client needs, but your core functionality is not changing. It's just how you're exposing it and how your client is to use it. So let's start one by one and understand how these interface segregation principles differ. How can we apply it? It is very common for you to run into an interface like this. I run a company and I want an interface for all the workers in my company. All right. This basically says that all the workers in my company are going to comply, are going to imply that they have all these properties and can actually undergo all these operations. Now, when we try to implement this class, we're going to try it for a full-time employee. And we hit our first problem here, is when we say at calculate worked salary, it does not make sense because the worker's salary in the case of a full-time employee is calculated on monthly salary plus other benefits. But if we're looking at the contractor employee, then we have something else that's a problem, which is that the net salary does not apply, and it's only the hourly rate times the hours a month that actually applies. This is their calculated work salary. Now, I know many people would think, what's the big issue? Well, think about it. Just we talked about in Liskov substitution principle, what you're doing here is you're basically introducing an interface and introducing surface area for error. You're introducing less area for change because you, more area for change, because you're basically saying that my interface does not represent the true need of the consumer or the implementer in this case. The problem here is you're going to end up with maybe 4, 10 types of employees, and each one of them is going to become unpredictable, knowing what it can support and what it cannot support out of that base interface. From a design perspective, this is a pure no-no. So how do we go about breaking this down? Let's find the true common thing between all workers, and that is the I-based worker. We know that every worker is going to have an ID, and everyone is going to have a name, and everyone is going to have an email. Part 2 is for the full-time worker salary. We're going to only give him the full-time worker salary. For full-time worker methods. And then we're going to go and have an I contract worker salary, which basically caters only for the stuff that is relevant to the contractor. We then have the class full-time employee, which knows how to calculate that based on being an I full-time worker salary and I contract worker salary. Do we have more interfaces? Yes. Do we have more code? Couple of lines. But what we don't have is an ugly exception running because the object itself cannot support what it has implemented from its interface. What we don't have is surface area for error. And what we do have is a true representation of a hierarchy that represents the real entity we are representing from real life. And this is where interface segregation principle says, have as many interfaces as you need to be as closer to the true thing as possible and reduce the surface area of forcing consumers to implement or have signatures for operations they do not simply support. All right. Any questions about this before we move on? All right. Dependency inversion. We're done with code. You know why I don't usually show code on dependency injection? Because everyone is doing it in one way, shape, or the other. If you're using Angular, C#, Java, Python, whatever it is you're using some form of dependency injection. Dependency injection must be one of the easiest things, and I'm happy that people are using it. Yes, we do have some people that have anti-patterns like service locator, which should not be used. But the reality is the idea among developers and architects that you should base your dependency based on abstractions and not on implementations has been something that the industry has been aware of for a while. We can argue over the techniques, over the containers we use, over how we do it. But when it comes to dependency injection, the definition is pretty simple. Do not introduce high coupling because you're basing your dependencies on implementations instead of modeling them on abstractions. Now, please note that any dependency is a debt. Any dependency over any kind of modules between others is a debt. We call it a technical debt. We call it a high coupling debt. So the idea is here, if you are going to take over a debt, make sure it's worth it and make sure you're getting your return over that debt and make that debt worth it. And the easiest way to do that is dependency injection. So I always say, just do it. Just do it. I think Nike actually came up with that motto just for dependency injection. Now, if you're looking from an electricity perspective, no one from you guys is basically sitting down wiring his stuff into the wiring inside the wall. What you have is an abstraction between you and the wall. You don't care what the implementation of the wiring is behind the socket. You're plugging into the socket and that's all that matters. You are abstracted from the complexity and implementation. You have no dependency on the wiring. No direct dependency, that is, of course, right? So what does it look like in our software? Imagine that you have an encryption service that reads from somewhere and writes to somewhere else the encrypted answer. If I basically build an encryption service all in one class, all tightly coupled together, what I'm going to end up with is a service that basically can do the one thing and cannot be extended in the future, cannot respond to change really. So I have three functions here. I have reading the input, encrypting the server, encrypting the input, and writing it to some sort of output. So instead of tying myself to the concrete implementation of these things, I basically introduce abstractions. So in this case, the encryption service will use a reader to read the input from the screen, from the file, from the database, from the stream, from the web service, it doesn't really matter. And then it runs the encrypt method and encrypts whatever I need it to, and then basically writes it wherever it needs to write it to. Now notice the encryption service itself, it does not care about the implementation. It does not care where it's going to get its input from, and it definitely does not care where it's going to write to. But what it does care about is the pure function of reading and writing. The implementation here is abstracted, meaning I don't have tight coupling, meaning I can introduce new forms of input and new sources of input in the future and further targets to where I can output to, right? So any questions on dependency injection? All right, we're almost done, guys, and then we'll open for questions. Now let's do some wrap up. S.O.L.I.D is important in general to understand. It's a small topic with huge application. It's a small tool set to learn, but it will feed into a lot of your design decisions, even when you get to building microservices at a high level, distributed systems at a high level, or simply writing a small calculator that basically calculates the interest of a loan or some mathematical algorithm. The way you think about your code once you understand it is going to differ. Please note that it's not only practitioners of object-oriented programming that do this. It's not like if you're doing OO, that's the only guys who actually do need the same concepts that S.O.L.I.D Design Principles have. In fact, if anyone has read into ASD or adaptive software development, which is basically a form of development that is continuous adaptation of the process that you work with to produce the actual code, you will notice that S.O.L.I.D Design Principles help you a lot in this continuous adaptation, because as the process evolves, your code needs to evolve, and the more compliant your code is with S.O.L.I.D Principles, the easier it will be to change. And remember, we said it in the first slide, that S.O.L.I.D actually got trended. It trended, it became a thing. It became something people are talking about in 2001 on the back of new collaborative methodologies coming up, like Agile, like Scrum, like all of these things. Why? Because these methodologies were based on change. And that's what S.O.L.I.D gives you. S.O.L.I.D gives you a simple rule set for your code to give it the ability to change. All right. So today is a small session, guys, just for it. Keep your code clean. And if anyone has any questions, I'm open to any questions for the next 20 minutes. Let me know.